Active galactic nuclei, or AGN in short, are essentially active supermassive black holes. They can actually drive powerful jets that we can observe, for example, in the radio. We can see it here, mostly through synchrotron radiation, essentially relativistic electrons that will spiral on the magnetic field created by essentially ionizing all the radiation here and making it spin. What we know is that even though we can think of a black hole as actually getting things in, actually the energy that is radiated can lead to expelling fuel and actually keeping massive galaxies really hot. And if you keep the gas hot, then it means you cannot form stars. So for massive galaxies, it's not necessarily that the gas isn't there, but more that these AGN can actually release and keep releasing so much energy that the gas is kept hot, and therefore it cannot form stars. In Physics 263, we will not go into the details of how impressive and amazing AGN are and their relation with galaxies, but it is important to point out that we know that there's some sort of coevolution between a supermassive black hole of a galaxy and the galaxy itself. What we know is that at least for some galaxies, they can have a dramatic effect in essentially shutting down star formation. And we can see evidence of it with observations in the X-ray, where we see some X-ray cavities and the radio jets essentially permeating through it. And we know that there will be regions which will be so hot, there's no way that galaxies will be able to form stars. But on top of that, we also know that specifically at the tips of radio jets, these radio jets can actually encounter molecular clouds, and in some conditions, they can actually lead to forming more stars. We also know that some stars actually manage to form around an AGN, and therefore the overall effect is sometimes confusing, and there's a lot of questions to be answered in terms of how AGN really quench galaxies and also how they keep them quenched. What is very clear, though, is that we find supermassive black holes in pretty much all galaxies. And it gets even more spooky because whenever we've been able to measure both the mass of the galaxy, or technically the mass of the bulge of the galaxy, and the mass of the black hole, they're incredibly well correlated. Essentially, the supermassive black hole knows about the mass of the galaxy. The more massive a bulge of a galaxy is, then the more massive the black hole it hosts, with impressively small scatter. And it seems like some of these relations hold up to even high redshift or very high look-back times, which led people to pose the question of what actually came first. And it is possible that at least for some galaxies, the supermassive black hole might have formed first through an exotic process that can make black holes form directly without ever going through a star phase. And they can actually get to a mass of something like 1 million solar masses straight away. So far, we've focused on processes that hacked internally in galaxies, such as supernova feedback and AGN. However, just like humans, galaxies can be affected by their environment. I'm showing you here a real example of the density of galaxies in the cosmos field, essentially 6 billion years ago, to show that it's definitely not uniform. And the same thing would go for humans, for example. If you look in the UK, essentially this is the density of humans, and you'll see that there are regions which are overcrowded, but also regions where essentially almost no one lives. Same thing goes for the universe. Now, just like for humans, the conditions in which you form and evolve will actually have some effect on what happens to you, and the same thing will go for galaxies. With humans, in principle, we have a choice, and we could, in principle, move from city to field, or we can move from a country to another, but galaxies cannot do that. And essentially, the region where they are born will set essentially where they're going to end up. In reality, galaxies that reside on different environments typically look very, very different. And if we think of the extreme in terms of clusters of galaxies being the cities of galaxies with thousands of them versus the field where we only have a few and perhaps small groups, then if you take a typical galaxy from each environment, they will look very different. If we look at the field, then typical galaxies will actually look like this, pretty much like the Milky Way. They are still forming stars. But if you pick a typical galaxy in a cluster, it will very likely look like an elliptical galaxy that has not formed stars for a long time. And actually, if you look at the transition, or galaxies that are coming from the field to the cluster, they will look like this. And They're referred to as jellyfish galaxies, and what you're seeing or witnessing here are very strong environmental effects that will actually transform a galaxy like this into a galaxy like this by, for example, stripping or removing its gas. But as the process happens, it can actually lead to more stars being formed. And the reason why you see this as blue is because gas is being stripped, but also stars are forming, and we can see O and B stars actually being stripped from the galaxy and leading a trail. In 263, we will not go into the details of the process, but it's important to understand that many things can happen to a galaxy that lead to galaxies and clusters being typically quenched or dead. On one hand, galaxies can be harassed by other galaxies that get very close to it, that can actually lead to removing some of the gas, for example. Galaxies can be strangulated, and this is quite a violent word, but what it means is that galaxies rely on getting fresh supplies of gas to keep forming stars, but if you strangulate a galaxy, what you're really doing is cutting it off from the fresh supply, and therefore the galaxy can only form stars with the gas that it already contains, and it's just a matter of time before it quenches. On top of that, when a galaxy enters a cluster, it can experience REM pressure stripping, and it can lead to observations like these. And essentially, as the gas gets stripped, sometimes you can even strip also clusters of newly formed stars. And the really important thing to fully understand galaxy formation and evolution is that all these environmental processes will be happening on top of the internal processes, such as supernova feedback and AGN feedback. And therefore, at very high densities, where galaxies experience all these environmental effects on top of internal effects, it is very, very easy to take a healthy galaxy that's forming stars into a galaxy that is quenched and that will look like an elliptical galaxy after a while. Ultimately, what we know is that high-density environments are incredibly harsh for galaxies. In the very early universe, they might have had the conditions to actually lead to some of the most spectacular star-forming events in galaxies. But nowadays, all the conditions mean that even if you're a healthy star-forming galaxy and you're still connected to the cosmic web and you're getting a fresh supply, once you move into a cluster of galaxies, and this is just gravitational interactions, there's no way a galaxy can just decide not to join the big cluster. Once that happens, not only the fresh supply is cut, but also galaxies experience all kinds of other environmental effects that will then transform galaxies like this into galaxies like this. Ultimately, environmental processes are responsible for establishing this very strong environmental and mass dependence of galaxies. This plot over here shows you that essentially galaxies with the most stars or residing in the densest environments are typically red and dead. And that also at a fixed environment, say even in the field or in a low density environment, if you pick a galaxy that already has a lot of stars, it is typically red and dead. And if you pick a galaxy that is low mass but is residing in a cluster, it's almost guaranteed to also be red and dead. This means that if you pick a galaxy that is either massive or that resides in a high density field, it will look pretty much like this, an elliptical galaxy. But if instead you pick a galaxy that is low mass and living in a low density environment, it will very likely look like a spiral galaxy. And therefore, if you know the mass and the environment of a galaxy, you can very easily predict at least the likelihood of how it would look like and their properties. And the reason for this has probably to do with the fact that mass essentially will correlate with internal effects, how susceptible you will be to supernova feedback and also to AGN feedback, while the location that you're at will actually correlate with the environmental processes that you're actually going to suffer. And therefore, if you have information about the mass and environment, you'll have information about the internal effects and the external effects, essentially allowing you to predict what will happen to the galaxy after billions of years.